Spin a top fast enough and something strange happens. Tilt it, let go, and it doesn't fall. Instead, its axis slowly sweeps around in a lazy circle, like it's tracing the rim of an invisible cone, completely ignoring gravity pulling it sideways. Stop the spin, and the exact same top falls over instantly. Nothing about the top changed except how fast it's turning. Somewhere in that spin is an equation that bends gravity's pull into motion nobody expects. This is symmetry. Let's find the exact rule that turns falling into sweeping, and see it again, spinning the entire Earth. Start simple. A top that isn't spinning at all, tipped at an angle and released. There's nothing subtle here. Gravity pulls and it falls. That obvious case is the key to understanding everything strange that happens once it starts spinning. Balance a top on its point, tilt it slightly, and let go without spinning it. Gravity acts on its center of mass, pulling straight down, and since that center of mass isn't directly above the pivot point anymore, the pull has leverage. The top rotates around the pivot and falls flat, exactly the way you'd expect any tipped object to fall. There's no mystery in this case. A force with leverage around a pivot point is called a torque, and here the torque does exactly what torques normally do. It makes something rotate faster and faster, straight down toward the ground. That torque is actually a vector, and its direction is stranger than it first looks. Take the arrow from the pivot to the center of mass and the arrow of gravity's pull straight down, and combine them with a rule called the cross product. The resulting torque vector doesn't point down, and it doesn't point along the top at all. It points sideways, horizontally, perpendicular to the plane containing both the top's axis and gravity. For a top that isn't spinning, this sideways pointing torque doesn't matter much, it still just tips over. But keep that direction in mind. It's about to explain everything. Here's the general rule connecting torque to motion. Torque is the rate of change of angular momentum. For a top with no spin, angular momentum starts at zero, and the falling motion itself is what builds it. Rotation appearing exactly where the torque points, around that same sideways axis, tipping the top over. There's nothing yet to redirect that torque into anything else. It simply creates the fall, moment by moment, until the top hits the ground. It's worth pinning down exactly how strong that torque is, since the number matters later. Torque equals the force, times the distance from the pivot, times the sine of the angle between them. Gravity pulls straight down with strength equal to mass times g, and the angle that matters is the tilt of the top's axis away from vertical. So the torque's strength works out to mass, times g, times the pivot to center of mass distance, times the sine of that tilt angle. Every one of those four quantities will show up again once the top is spinning, and one of them, the sine of the tilt angle, is about to disappear in a surprising way. Now spin the same top fast before tilting it. That spin creates something the stationary top never had, a large angular momentum vector already pointing along the axis before gravity gets involved at all. A spinning object carries angular momentum, a vector quantity pointing along the axis it's spinning around, with a direction set by the spin's rotation using the same right-hand rule as before. Point your fingers in the direction of the spin, and your thumb gives the direction of this vector, called L. The faster the object spins, the longer this vector gets. For a top spinning quickly, L is large, and it points straight along the tilted spin axis, from the pivot up through the top's body. This vector is what a non-spinning top never has, and it's about to change everything about how torque behaves. The size of this angular momentum vector depends on two things: how the top's mass is distributed, called its moment of inertia, and how fast it's spinning. Multiply those together, and you get L. A top spinning twice as fast has exactly twice the angular momentum, same direction, same axis, just a longer vector. This single number, how large L is compared to the sideways torque from gravity, turns out to be the entire difference between a top that falls over and a top that gracefully sweeps around in a circle. So here is the actual situation for a spinning, tilted top. A large angular momentum vector L pointing along the tilted axis, a pivot point at the bottom staying fixed, and gravity still pulling down on the center of mass exactly as before, creating that same sideways pointing torque vector. Nothing about the torque has changed. What's changed is that now there's already a large L vector sitting there for the torque to act on. One honest caveat: a spinning top also picks up a small amount of extra angular momentum from the precession itself, not just the spin. For a top spinning fast compared to how quickly it precesses, that extra piece is tiny, which is exactly the approximation used here, and exactly why the result works best for fast, confident spins rather than slow, wobbly ones. Here's the entire secret in one geometric fact. The torque vector and the angular momentum vector point in completely different directions. And when a vector is pushed sideways instead of along its own length, it doesn't grow. It turns. Look at the two vectors sitting at the pivot, L pointing up along the tilted spin axis, and torque pointing horizontally at a right angle to the vertical plane containing that axis. These two vectors are perpendicular to each other, always, no matter which direction the axis currently happens to be tilted toward. That single geometric fact is the whole reason precession exists. A push directly along a vector's own length makes it longer. A push perpendicular to a vector doesn't make it longer at all. It rotates its direction instead, the exact same way a sideways gust of wind doesn't speed up a moving arrow. It curves its path. The precise rule is that the change in angular momentum over some tiny slice of time points in the exact direction of the torque, and has a size equal to the torque strength times that tiny time interval. Since torque points perpendicular to L, this tiny change gets added on sideways, tilting L's direction by a small angle without changing how long it is. A moment later, L points in a very slightly new direction, still the same length, and the torque, still perpendicular to whatever direction L currently points, immediately starts nudging it sideways again. Do that nudge continuously, always perpendicular, always the same length of L, and the tip of the vector traces out a perfect circle instead of ever tipping downward. The spin axis itself sweeps around, tracing the surface of a cone in the air, with the pivot point at the cone's tip. This sweeping motion is called precession, and it's the direct geometric consequence of a torque that never points along the vector it's pushing on, only ever sideways to it. Precession isn't just a curiosity, it has an exact rate, and that rate hides a genuinely strange fact about spinning tops. To find how fast the axis sweeps around, picture looking straight down from above at the circle the tip of L traces out. That circle has a radius equal to L times the sine of the tilt angle, the horizontal component of the tilted vector. Meanwhile, the torque vector's tip moves along that circle at a rate equal to the torque's own strength. Divide how fast the tip moves by the radius of the circle it's moving around, and you get the angular speed of the sweep itself, the precession rate. This only works cleanly because torque and radius are both measured over the same tiny instant of time. So the ratio between them settles into a constant rate, rather than something that drifts as the top keeps turning. Work through the algebra, and the tilt angle appears in both the torque strength and the radius of the circle, and it cancels out completely. What's left is remarkably simple. The precession rate equals the top's mass times gravity times the distance from pivot to center of mass divided by the moment of inertia times the spin rate. Notice what's missing. The tilt angle isn't in the final formula at all. A top precesses at the same rate whether it's nearly upright or leaning almost flat for a given spin. That's not obvious from the setup, and it falls straight out of the geometry. And because spin rate sits in the denominator, spinning the top faster makes it precess slower. A top spun hard looks almost motionless and upright, sweeping around so slowly it's barely noticeable. A top spun gently wobbles through a fast, wide precession you can watch happen in real time. The relationship is exactly inverse. Spin a top 10 times faster, and its precession rate drops to 1/10 of what it was. Not some rough approximation, the same ratio, flipped upside down. Same top, same gravity, same torque. The only thing that changed is how much angular momentum there was to redirect. Friction always wins eventually, and the same equation that describes a dying top also describes something vastly larger, the planet you're standing on. Real tops rarely trace a perfectly smooth circle. The steady, clean precession only happens if the top is released with exactly the right sideways motion already built in. Let go of a real top from rest, and gravity gets a brief head start before the precession fully catches up, so the axis first dips slightly before curving back over and over, tracing a looping, scalloped path instead of a clean circle. This extra wobble is called nutation. As the spin slowly bleeds away to friction, the precession rate, which depends on 1 over the spin rate, climbs higher and higher, the sweep visibly speeding up and widening in the top's final seconds. Eventually, the spin rate drops so low that the angular momentum vector is no longer large enough to keep redirecting into a stable circle. At that point, the top's behavior collapses back into the very first case. Torque simply builds angular momentum in its own direction again, and the top tips over and falls exactly the way the non-spinning top did at the very start. Precession was never a separate kind of physics. It was the same torque, temporarily overpowered by a big enough L. This exact resistance to being tipped over is put to work everywhere. A spinning bicycle wheel resists leaning the same way a spinning top resists falling, which is part of why a moving bike is easier to balance than a stationary one. Ships and aircraft carry actual spinning gyroscopes wired into their navigation systems, because a fast spinning wheel holds its angular momentum vector pointing in a fixed direction in space no matter how the vehicle rotates around it, giving a stable reference direction even in rough seas or turbulent air, entirely because of the same physics keeping a top upright. Earth itself is not a perfect sphere. It bulges slightly at the equator from its own spin, and the Sun and Moon's gravity pull on that bulge with exactly the same kind of sideways torque acting on a tilted top. Earth's enormous spin angular momentum keeps that torque from ever tipping the planet over. Instead, Earth's axis slowly precesses, tracing out a cone in the sky over roughly 26,000 years. The same formula, the same geometry, just scaled up from a tabletop toy to an entire planet quietly sweeping its axis through the stars. So a spinning top doesn't defy gravity, it outmaneuvers it. Torque always points sideways to angular momentum, so instead of falling, the axis gets rotated into a cone, sweeping instead of tipping. Spin faster and it sweeps slower. Let the spin run out and gravity finally wins, the same way it always would have. And that exact equation, run on a planetary scale, is why Earth's axis has been quietly tracing its own enormous circle in the sky for the entire history of civilization. If you want more ideas like this, explained from first principles, subscribe Symmetry. See you in the next one.